Hey everyone, today we're going to start section 3, and specifically we're going to talk about mechanical advantage and efficiency. Now remember in the last section we talked about and defined a machine. We said a machine is anything that changes the force of something and it makes tasks easier to do. Well, mechanical advantage is going to tell us how much easier does a machine allow us to do things. It's defined as the number of times the machine increases the input force. And all that means is if you put in a force of 5 newtons, will it double the 5 newtons, triple it, quadruple it? One thing to know about mechanical advantage is the higher the mechanical advantage, the less force that you have to apply to a machine. So if you have a good machine that's working well, that has a good advantage for you, you can do as little amount of force as you want. Now, there are two types of mechanical advantage that we're going to talk about. The first one is actual mechanical advantage, which is often abbreviated AMA, and it's determined by measuring the actual forces acting on the machine. Now, when I say actual forces, I mean things like gravity, friction, air resistance, buoyant force, all of these. If we were given an example of a ramp, one ramp is rough surface, the other one is a smooth surface. We have to take into consideration all of the forces. And we learned that friction happens when two surfaces rub against one another. So if you're trying to push something over a rough surface like a carpet, it's going to be a lot harder than if you were to push something over a smooth surface. That means if we're talking about the mechanical advantage of a ramp, a rough surface is going to be less than a smooth surface, and that is because you have to use more energy and more work to overcome friction. So AMA equals the ratio of the output force to the input force. The equation is just listed below, and in terms of our units, because those are important, force is usually given the unit newtons. So both our output and input will be newtons since they are forces. And there's no unit for an AMA. And the reason for that is because newtons divided by newtons cancels those out. So you don't have a unit. We're going to do an example of calculating AMA. At the top, I wrote the formula. It's output force divided by input force. It reads, Marshall wants to remove a tree stump from the ground. To do this, he puts the end of the long beam under the stump and puts all his weight on the other end. His weight is just enough to lift the stump, and the stump weighs 400 newtons while Marshall weighs 250 newtons. What is the actual mechanical advantage of the lever that Marshall is using? Most people understand the equation, but where they get stumped is they see two sets of newtons because I'm working with two different types of forces. They often struggle with where to put those forces, as an input force or an output force. And the biggest hint I can give people is remember, input force is what you put into the machine. So what are you doing in terms of the machine? And here we're talking about a beam. The output force is what the machine puts out. So what is the machine actually allowing that person to do? So if we think about it in terms of that, AMA, the output force is going to be 400 newtons because the machine is actually lifting the stump. That's what we're getting out of it. Divided by Marshall's weight, which is 250 newtons. This is the input force because this is the amount of force he's able to put on the beam. All we have to do is divide those two things. So if you take 400 divided by 250, you get 1.6. 1.6. And I asked my kids in class today, are we done? And hopefully you said, yes, we're done. And the reason for that is because AMA does not need a unit. My newtons and my newtons cancel. The other type of mechanical advantage we haven't talked about yet is ideal. It is abbreviated IMA, and it's where there is an absence of friction. The equation is a little bit different. First, please note that the input distance divided by output distance. We're not working with forces anymore, we're talking about a distance. Also, please note the input and output has now flipped. When we take a little bit closer look at that equation, there are a couple different ways that we can describe input and output distance. And often we call the input distance the horizontal distance, and the output distance we call the vertical distance. So remember, horizontal means like if you go across something, so it's left to right, while vertical distance, this is going to be up and down. So do you raise something? Do you lower something? If we think back to units, distance is measured in meters, which is given as a lowercase m. And because we're taking meters divided by meters, these cancel again, so IMA does not have a unit. If we look here as an example of IMA, so let's write our equation up here so we kind of know it. IMA equals input distance divided by our output distance. It reads, a woman drives her car up two wheel ramps to perform some repairs. If she drives a distance of 1.8 meters along the ramp and raises her car 0.3 meters, what is the ideal mechanical advantage of the wheel ramps? So IMA is going to have to deal with our input and output distances. And we're given 2 meters, so we have to figure out which one is our input and which one's our output. If you recall, our input we said is also known as horizontal. So if you go along a ramp, means you're going to go left to right. That means my input distance is 1.8. My output distance is also known as my vertical distance, and here we can see that the car is being raised. So that's up and down. That can go in for my output distance of 0.3. When you take 1.8 divided by 0.3, this gives me a difference of 6, which ends up being my final answer because IMA does not need a unit. My meters and my meters cancel each other out. Now, if I give you the equation, I want you to be able to rearrange it and solve for any other piece of it. So if I give you IMA and output distance, I want you to be able to solve for the input distance. We're going to do that here with this example. So remember, IMA equals input distance divided by output distance. And we just need to plug in what we know. Well, here it says the IMA is 2.5, so let's plug that in at the 2.5 side. It says my output distance is 10, so let's put that in for my output distance, or 1 meter. And it wants to know the input distance, so we're going to put X in for that. Now we have it set up all pretty that we can cross multiply and divide. So X times 1 gives me an X. 1 times 2.5 gets me 2.5. And then I ask my kids, are we done? And sometimes they stumble and they say yes, but they forget we're not finding IMA, we're finding distance. So here I have to have a unit, which is meters. So now that we've talked about the two differences, how does AMA compare to IMA? Well, because friction's always present in AMA, it's going to be less than ideal mechanical advantage because ideal mechanical advantage does not have any friction. So because friction does reduce mechanical advantage, engineers try to design machines that use low friction materials and lubricants. Here we have a picture of 2 lubricants, WD-40 and what you can put in your car. Also, low friction materials, we have ball bearings here because we're going to replace sliding friction with rolling friction anywhere that we can. The second part of the lesson we titled efficiency. So let's kind of hit on what is efficiency. It is the percentage of the work input that becomes work output. Oftentimes you hear people talk about the efficiency of a heater running, or how well does it heat up a house, the fuel efficiency of a car. It just tells us how well our machine is functioning and producing the work that we want to see. So efficiency is usually expressed as a percentage, and actually in your notes I put always, just for your purposes. The equation is work output divided by work input times 100, and multiplying it by 100, that's what allows us to get our percent sign. So if I said the efficiency of a machine is 75%, I know that 75% of my work input is actually becoming work output. A good example of this, if you put in 100% of the work and you only have a 75% efficiency, that means 75% of the work you're doing is actually being converted. Here's an example for efficiency. So again, we're going to just go ahead and jot down the equation. Efficiency equals work output divided by work input times 100. And you just plug in what you know. What is efficiency? Well, efficiency is X. Work output, we're going to see, is 35 joules. Work input is 40 joules. We're going to multiply that all by 100. So if you do 35 divided by 40 times 100, you're going to see that this comes out to be about 87.5% efficient. So this is a relatively pretty efficient machine. The other way, I want you to be able to rearrange this equation as well and solve for the other parts. It says, what is the work output of a machine that has a work input of 10 joules and efficiency of 75? So our equation, efficiency equals work output divided by work input times 100. If you read this, you find the efficiency is 75%. The work output, we don't actually know that. The work input says 10 joules, and then we put times 100 at the end. Most people see this and they kind of freak out, but it's pretty simple to solve. We're going to divide both sides by 100. And when I divide both sides for 100, it cancels out on this side and leaves you with the following setup. And if you see this is easy because all you have to do is cross multiply and divide. So if you cross multiply, 75 times 10 gets me 750. 100 times 10 gets me 100x. And if you divide that all by 100, 750 divided by 100 gets me a 7.5 for my work output. So here, if I'm trying to find work output, this gives me it in joules. So why is the efficiency of a machine always less than 1? Well, if you recall, work output is always less than work input. So if work output's on top of a fraction, it's always going to be less than. But the real reason we can explain this is that there's always some type of friction involved. Machines cannot run 100%. So again, just like what we've been talking about, we're going to try to reduce the friction as much as possible. We can do this by increasing the efficiency of a machine. Anywhere we can change sliding friction to rolling friction, we do it. Any time we can use low friction materials like a slick surface or a slick piece of fabric, we're going to be able to do that. And then just know that we can lubricate things with grease or other lubricants like WD-40 to help as well. And then it ends on this slide that shows engineers analyzing the flow pattern of a smoke trail to determine the air resistance that acts on vehicles, because they want to be able to maximize its speed but also the fuel efficiency that cars have. And that's the end of today's lesson. Let me know if you have any questions, and I should be more than happy to help.